Hello. Now we will look at indices or powers, particularly in the context of writing things in power notation, which is useful in certain parts of the course. So power notation means we write the variable, usually x, to the power of some power. So in this case I've written it as n, but it could be a fraction, it could be a decimal, it could be lots of different messy things, but we're going to write x to the power of something times whatever its coefficient is. The coefficient does not generally need to be written in power notation. It can just sit as a normal coefficient, so as a number just sitting next to our x. But we need the x all consolidated together to a single power in power notation. And I'm going to label that as capital P, capital N as we go on. Anytime we have to deal with complex indices, we are always going to open up page 21 in our log tables or formula tables. That's going to show us all of the tools we have available for both indices, powers or exponents, and logarithms. Now let's get into it. So here we have x divided by the cube root of x. And we want to write this in power notation. Well, this x here is just x to the power of 1. So any number or just left by itself, including any letter, is just to the power of 1. And the cube root here, the cube root means to the power of a third. So we can see that rule down the middle of our page here. Root q of a means a to the power of 1 all over q. So that's the same as we've got here. So we have x to the power of 1/3. And the argument for this is, what number would you multiply by itself 3 times to end up with x? Well, you know, when you multiply the same base, you would be adding the powers. So you'd have a third plus a third plus a third would give you 1. That's where the logic of this rule comes from. Now, when we are dividing the same base, we can subtract the powers because we're essentially cancelling out a particular number of x's. So we have x to the power of 1 minus this power of a third. So we can write that as x to the power of 3 over 3 minus x to the power of a third. So we end up with x to the power of 3 minus 1 all over 3 is x to the power of 2 all over 3. So that is a very fully written out version of the power notation for that. So that is written in power notation. If we were to write that for a final answer in an exam, we would generally not leave it in this form. So that is power notation. So if I leave that, that is in my power notation. If we want it as a final answer, we would say, well, this is the same as x to the 2 times 1/3. So if we're multiplying the powers, that means we had a power in the bracket. So that means x squared to the power of a third, which would be the cube root of x squared. So that's how we might be expected to do it for a final answer in an exam. But if we need it in power notation for whatever reason, that's how we would use it. That's how we would write it. If we have a look down here, we have 6x root x. So let's write this all out using powers. So we'd have 6 times x to the 1 times x to the half. So the square root, the one that we don't bother writing a number in for here, has a hidden little 2 because this is the most common one. It becomes the default and therefore we don't bother writing 2. You can if you wish to in an exam. Just be careful you don't get confused with it being multiplied by 2. Now we have this written in powers. Well, I have the same bases multiplied together, so that means that I can add the powers. So that means, and the coefficient just comes along for the ride. So I have x to the power of 1 plus 1/2, which is 6. Should have equal signs here. 6 times. The bracket is just to clarify that we're dealing with the x's. You don't actually need to write it in unless you particularly wish to. It just clarifies we're dealing with this stuff and the 6 is really just on the periphery. We're not worried about it too much. X to the power of 2 plus 1 all over 2. 6x to the power of 3 all over 2. And if we, and for our final answer, so that's in power notation. for our final answer, or we'd say that's 6 on x cubed by 1/2, which would be 6 on the square root of x cubed. So we can say 3 over 2 would be the same as 3 times 1/2, in the same way as we said 2 over 3 would be the same as 2 times 1/3. So here we have slightly messier indices to deal with. So we want to write this in power notation. So we need the x on the top line and we need it to the power of something. So we have 2 power of, this means power of 1/3. So I have x to the 5 power of 1/3. I can multiply my powers and do 1 all over 2 x to the power of 5 times 1/3 is 5 over 3. Now, if I move this up onto the top line so that it's what I want for power notation, that it needs to be on the top line, I can see that I can use this rule in the middle of my line here. A to the minus p would be equal to 1 all over p. If I change the line that the thing is on, I change the sign of the power. So that means that's going to be x to the minus 5 all over 3 all over 2. Or as we might more commonly write it, so this is in power notation, but as we might more commonly write it for power notation, we'd have 1/2 times this. So you can imagine that this has a denominator of 1. So x to the minus 5 over 3 has a denominator of 1. Multiplying that by 1/2, top by top, bottom by bottom, would get you back to this line. But it's often more helpful to have the coefficient out separate when writing in power notation. So that's in power notation. If we wanted, well, actually in this case we don't need to rearrange because that's what it will end up simplifying back to. So there's no value in this particular case in rearranging. It would just go straight back to what we started with. So that's what we need for that one. Here we have a little bit of multiply to do. You could leave this in surd form, that is to say with the square roots. I'm going to rewrite it in power notation to see how we use our power rules for it. So we have x to the power of 1/2 plus 1 all over x to the power of 1/2 on x to the power of 1/2 minus 1 all over x to the power of 1/2. What we should recognize here is that we have difference of two squares. We have a plus b times a minus b. So we know that when we multiply this out, we should end up with this squared minus this squared minus this squared. So we need to rewrite these in power notation, or I'm going to rewrite these in power notation before I go ahead. So if I change the line that this is on, I'm going to change the sign. So minus 1/2 minus x to the minus 1/2. And now I multiply these brackets out as normal. They are just normal brackets, just with more unpleasant indices than we often have to deal with. Plus x to the minus 1/2 on x to the 1/2 minus x to the minus 1/2. So we multiply these together. And when we're multiplying them, we're going to add the powers. So this is going to be x to the 1/2 plus 1/2 minus x to the same basis. So we have x to the 1/2 minus 1/2 plus x to the minus 1/2 plus 1/2. Multiplying these two together, I add the powers. Minus x to the minus 1/2 minus 1/2. So again, all I'm doing for all of that is I'm multiplying by the same base number. X is the same base for all of them. So I end up adding the powers. So I have 1/2 plus 1/2 is 1. Minus x to the power of 1/2 minus 1/2 is 0. Plus x to the minus 1/2 plus 1/2 is 0. Minus x to the minus 1/2 minus 1/2 is minus 1. Now, this is just going to sum to 0 anyway, but x to the power of 0 would always be 1. So a to the power of 0 is 1. This is one of the rules here, and we just need to know that by heart, effectively, that is always going to mean 1. That comes up in several different contexts throughout our work. So that sums to 0, and we're just left with x to the 1 minus x to the minus 1. So that would be it in power notation. And you would be able to rearrange it as x minus 1 all over x. When you have a negative power here, to make it positive power again, you'd put it underneath the line. And that would be our final answer in an exam, and that is written in power notation. Let's have a look at this one. So we have a power of 4 on this bracket. So what's going to happen is that we'll rewrite this in power notation, and then we're going to put the power on each term inside the bracket. 4x, that's going to be the power of 1 on 2 on, this is power of a half. This is x cubed to the power of a half, power of 4, or x to the 1 all over. We'll tidy this up first. 2 x to the 3 by a half is going to be 3 over 2 to the 4. Now I can use my rule here. So I'm distributing my powers, and I also have a power on the bracket, so that means I'm going to multiply my powers in this case. So I have 4x to the 1 all over 2 to the 4 times x to the 4 times 3 all over 2. Or an x to the 1 all over 2 to the 4 is 16. Now, 4 times 3 over 2, well, I have a common factor of 2, so I end up with 2 by 3 is 6. So this is x to the power of 6. Now, I have division that I can do here, so I can divide above and below by 4, or take out a common factor of 4. And here I can subtract the powers because this is the same base number. So I have x to the 1 minus 6 all over 4. And if you want to put a 1 there, you can. So I have x to the minus 5 all over 4, or more commonly, as I say, we would write the coefficient next to it. So that would be the same as a quarter of x to the minus 5. So that's it in power notation. And as a final answer in an exam, we would tend to bring the negative power down to make it positive again. So we'd have 4 all over x to the 5. But that's it in power notation. Now, finally here, we need to write this in this form. So we see here that we need to write this as a single fraction. So I need to get the same denominator. So I'm going to tidy this up as much as I can to see how I would get my lowest common denominator. So I have, this is going to end up being x to the 3 over 2, because I have x to the half multiplied by power of 3. And then that's times 1 for our power here. So that's going to be x to the power of 3 all over 2 plus 4x to the power of 1/2. Not too worried about what's on the top line unless I can see an easy simplification. When I tidy up, I say, well, what do I need to multiply by here? Well, this is essentially a 2.5. 5 over 2 is 2.5, and this is a half. So if I multiplied this one by x squared above and below, then I'd get the same denominator. That lets me write that as a single fraction, and I see I want to end up with a single root x here, so I need to break this up. And